My name is Franklyn. I'm affiliated with 0xPark and Harvard University, and today I'm going to be talking about Ecne, the first ever verifier for ZK-arithmetizations. First, I want to talk a little bit about zero-knowledge proofs and ZK-SNARKs. This is hopefully mostly review, but I just want to talk about the components that are most important for understanding Ecne. So zero-knowledge proofs allow you to prove that you possess a secret x, so that f of x equals y, where f is a known function, and we refer to these as circuits, and y is a known value. So an example that I think is very good, illustrative of this is the function f might convert private to public keys. So x is your secret, it's your private key, and y is a public key. So how do you prove that you want a public key? Classically, this is done with a signature. And what's really cool is that as this field developed historically, people came up with all these functions f and their very own zero-knowledge proofs for them. But then ZK-SNARKs emerged, and ZK-SNARKs let you do this for any function f. So we don't have to come up with functions f, create ZKPs for those bespoke. We can just do ZK-SNARKs, and those will give us zero-knowledge proofs for any function. Okay, so the ZK-SNARK stack has a lot of components. There's like a diagram online that you can see that has like 6 or 7 layers to it, but the ones we care about today are a witness generation procedure and a set of constraints. And these are both generated in the programming language given by CIRCOM. Okay, so first, let me give some definitions. So x will be used to represent the input, and this is the input to the function. Y is the output, which is the output of the function, and z is the witness, and these can be thought of as corresponding to auxiliary variables that are used in the function. So the witness generation process is just something that generates a y and a z from a value of x, and the constraints are going to be called a QAP, a quadratic arithmetic program, or in R1CS, a rank 1 constraint system. So this is going to be given as a set of degree 2 equations of this form. So like a1 times d1 plus a2 times d2 dot 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 plus an times dn multiplied by b1 d1 plus b2 d2 dot 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 through bn dn equals c1 d1 plus c2 d2 dot 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 cn dn. And di here correspond to variables among the set x, y, z. And as with most things in cryptography, all of these equations are taken over a finite field. So ZK-SNARK construction involves 2 phases. The first phase is converting the function f into a QAP. And this is what we mean when we refer to an arithmetization, because you're converting some function f, which may or may not be like a mathematical function, and you convert it into this QAP format, which is very much like a mathematical format. And this conversion is often done manually. So you'll specify in code what constraints you want to encode. And a second, we convert this QAP into a ZK-SNARK. It turns out that once we have the QAP, the conversion into a ZK-SNARK is relatively more straightforward. And the reason we have the QAP is because the QAP form of a function is particularly easy to encode into a zero-knowledge proof. So now let me give some examples of QAPs. So this is a relatively simple one, but the statement y equals x cubed is equivalent to the statement that there exists an x2 such that x2 equals x times x and y equals x2 times x. And the way you might prove this is by noting that if there exists an x2 so that x2 equals x times x, well then x2 is uniquely determined as being x times x and y must equal x cubed. So here we've shown that the classical function y equals x cubed is equivalent to the statement that there exists an x2, which is the witness here, so that x2 equals x times x and y equals x2 times x. So this is a relatively simple example of a QAP, but hopefully it shows that this form makes sense. Okay, now here's a slightly more complicated example, which hopefully kind of motivates this, because it shows that QAPs can be rather complicated. So here z is an array of size 2, and y is z indexed at location I. Okay, and this is equivalent to the statement that there exists E0 and E1, so that E0 times I is 0, E1 times I minus 1 is 0, E0 plus E1 is 1, and y equals E0 times Z0 plus E1 times Z1. Okay, and the way you prove this is actually quite interesting. So if you look at E0 times I is 0, if you imagine I being equal to 1 here, E0 would just be equal to 0, right? And so all but one of these variables, E0 and E1, must equal 0. So then with E0 plus E1 equals 1, we would be able to solve for E0 and E1, and then using y, we could just finish that off, right?
Mm-hmm.
And so I said that this is a conversion from a function into a QAP, but that's not entirely correct. Does anyone see what's wrong with this? This is very subtle, but if you are eagle-eyed, I think you might have been able to spot it. Anyone want to take a guess?
Do we need to have another set of equations for E1 times I equals 0? And then E0 times I minus 1 equals 0 as well?
So, okay, maybe I should state my question in a slightly different way. So, as stated, this system of equations here is not actually a QAP. So why is it not a QAP? It's not about like, does this satisfy, like these statements are equivalent, but strictly speaking, this is not a QAP. And why is that?
Can have subtraction?
Subtraction's allowed. Jan, I think you might be on the right track, but could you provide a little more detail? Okay, so I guess the reason that this is kind of this is a very minor point, but technically in a QAP, you need to have like the left-hand side should be a linear thing and the right-hand side should be the product of two linear polynomials. So here, this is E0 times E0 plus E1 times E1, which strictly speaking is not the product of like 2 degree 1 polynomials. It's easy to convert this into an R1CS form, but technically speaking, it's not.
Mm-hmm.
Okay, so this is also a time I think I should ask for questions. So does anyone have questions about what I've covered so far? Is it clear like how a function converts into a QAP?
So,
or that like, yeah.
So in this case, when you specify the equation on the right-hand side, don't you need to specify the range of I as a constraint? Right now, you're assuming that I is going to greater than 0 and less than 2, right?
That's a very good point. Yes. So here, if like I is not between 0 or 1, this equivalence is false. So technically, if I is like out of the range 0, 1, y equals zi is like, I guess probably not a well-formed expression. And in particular, there is no value y that you can state that is equal to z of I. And likewise, there will be no solution to this system of equations. But yeah, you're absolutely correct. And technically, for this y to always give an output, you need I to be constrained in 0 and 1. Mm-hmm. This is an issue that will crop up later.
All right. Any other questions from the audience before Franklyn switch to the next?
Yeah. Step? Also, feel free to interrupt me at any time if you have questions.
Mm-hmm. Yeah, I think we can move on.
Yeah, I think we can move on too. Cool. So in order to make sure this zk-SNARK is secure, this translation from between function and QAP must be exactly right.
Mm-hmm.
Like if there's even a slight issue, this zk-SNARK might just not work. And in ZK, it's of paramount importance that this conversion is correct, because it turns out if there's a hole, it might be exploited in the wild. And then due to the way ZK is designed, we might never know that that it's been exploited, because zero knowledge will kind of hide some of the transactions. So in ZK, it's like really, really important that this conversion is correct. Okay, and unfortunately, QAPs are usually constructed manually, which really leaves open the possibility of polls when this QAP is not equivalent to a function. So to show some examples where this has actually happened in the real world, note that there have been holes in well-known ZK circuits. So for example, Dark Forest, a common online game, had a missing bounds check, and Aztec's non-native field arithmetic also had a missing bounds check, which meant that this QAP was not equivalent to a function. To really drive this home, these bugs will often appear completely without warning. So let's look at these two programs in SIRCOM. So this is the dreaded range check program, which, as we've seen, has been the Achilles heel of a lot of other programs. So this range check works by, you have an input X and you want to bound X between two values. Here you want to bound it between like 0 and 3. And the way you do this is by writing out a binary representation. So you write out that out 0 times 2 plus out 1 is equal to X, and that out 0 times out 0 minus 1 is 0, and out 1 times out 1 minus 1 is equal to 0. These constraints mean that out 0 belongs to the set 0 and 1, and out 1 belongs to the set 0 and 1. As a consequence, 2 times out 0 plus out 1 must be equal to X. So since each of these numbers is between 0 and 1, then X must lie between 0 and 3. Okay? So in the second example, we have an input X, we have output of size 3, except this time we made a typo. Say we made an off by 1 error when specifying this. And now we have out 1 times out 1 minus 1 equals 0, out 2 times out 2 minus 1 equals 0. So in this case, there is actually no constraint on X, because out 0 can be anything, and out 1 is either 0 or 1. Since modular inverses exist, X can literally be anything here. And if you compile this with SIRCOM or any of the existing tools, they won't tell you that anything's wrong here. They will just say pass. However, Ecne will tell you the difference. Okay, so in this case, the good case, it'll tell you X is uniquely determined. This is true because X is like an input, so you know what it is, and X is bounded between 0 and 3. Likewise, out 0 belongs to the values 0 and 1 and is bounded between 0 and 1. Out 1 is bounded between 0 and 1 and lies between 0 and 1. And otherwise, and in this bad case where we have the out 1 and out 2, we again have that X is uniquely determined because we know the value of X as an input. But here you'll now see that there is no bound on X anymore. And all these other variables, out 2, out 0, out 1, are not uniquely determined. So Ecne is able to distinguish these and thus constitutes the first ever verifier for these QAPs.
So I think we have a question from the audience. Why are no constraint on out2? I guess out2 doesn't exist, so which means that whatever you wrote is essentially like not very meaningful. In the sense, even if you write a constraint for out2, it's just like no op, right? Yeah,
exactly. But yeah, that's a good point. Here, like out2 is not constrained. Like strictly speaking, this is not like a valid circuit because you're right, the output's not all uniquely determined, but this is just simplified for the sake of exposition. But thank you for keeping me honest. Okay, so now I'm going to define some notions of weak to strong verification, which we'll seek to prove here. So the first notion is weak verification, and this is when a system of equations has at most one unique solution for the output variables, given the values of the input variables. There's witness verification, which is when a system of equations has at most one solution for all variables present in the system. So not just the output variables, but all the variables. And the last one is strong verification, which is closest to the notion of formal verification that I think you guys are familiar with. It's when a system of equations maps to a formal mathematical expression. And this will often require like a lot of complicated specifications that aren't necessarily naturally generated in the process of writing your circuit. So it's often the hardest one to prove, and indeed Ecne will only focus on weakened witness verification. So it's not obvious, to me at least, why we would care about weak verification. And there's a tricky argument that is needed to show that weak verification is useful. So let me write this out. Broadly, the goal is to show the equivalence between f of x equals y and that there exists a z so that a of xyz is true. Okay, and here a of xyz is just the QAP that we have. So this is a statement that several algebraic expressions are equal to 0. Okay, and this is the goal of what we're trying to do. We're trying to translate a function into a QAP. And weak verification would tell you that given the value of x, there is at most one value of y so that a of xyz is true, and potentially more than one value of z. This is the definition of weak verification. So if you run the witness generation procedure, you generate a y and a z, okay? And if this satisfies a of xyz being true, then we have something called witness satisfaction. Okay, and I'll talk about that a little later. So now, if we have witness satisfaction, then we've shown that only one specific value of y can work, and we've found that value of y. Thus, and that means that we have found the only value of y that works, and thus we've established this equivalence for a specific value of x. And if this were true for all x, then we would have this equivalence.
So,
okay, your question?
So, Franklyn, I have a quick question. In this case, I understand that y is the output, but are you assuming that those z are all correspond to the witness variable?
Yes, that's the definite. Yep.
And then when you say weak verification, are you only ensure that the uniqueness of y, in the sense that there was at most one value for y, but there's no constraint over z at all?
Yes.
Okay. But
indeed, some people, sorry.
But I'm assuming that you eventually have to enforce the uniqueness of z also, right? Otherwise, there might be a different kind of model that will also satisfy your equations, but you might get different z. Are you also checking that? Or are you just checking the on the y?
I am, so yeah. You're referring to witness verification, right? So this is when it has at most one solution.
Yeah.
So sorry, I'm a little under the weather, but knowing that y equals f of x, or knowing that like weak verification is true, is already enough for you to show this equivalence given like witness satisfaction. Later on, we'll talk about what happens when you don't have witness satisfaction.
Okay.
And there, indeed, witness verification becomes useful.
Okay.
But if you can always get a y and a z that work, and you know y is unique, then everything's okay. So why do we need to prove that z is unique? You'll see, if we have witness satisfaction, we don't need to show that z is unique, but there are some cases where we won't have witness satisfaction. All good?
Yeah.
Cool. So now let me just briefly talk about witness satisfaction a bit. This is saying that y and z generated from x satisfy a of xyz and y equals f of x. Note that this is something we can test with stress testing, right? Like, let's just get lots of random values of x, get a y, get a z, and if a of xyz is true and y equals f of x, then everything's good, right? Okay, so now let me talk about the differences between the various types of verification with an example. Say that we have a QAP that purportedly implements like big integer multiplication with inputs x1, x2, x3, y1, y2, y3, that outputs z1, z2, z3. So here, z1, z2, and z3 are the outputs of multiplying the number represented by like x1, x2, x3 by y1, y2, y3. So showing weak verification of this QAP would be showing that the output z1, z2. Someone asking a question?
Yes, if you are not asking a question, please unmute yourself.
Yeah.
If you please mute yourself.
So weak verification here would be showing that the output z1, z2, z3 is uniquely determined given the values of x1, x2, x3, and y1, y2, y3. I apologize for using z for both the witness and the variables here. The witness verification means that all intermediate outputs of this QAP are uniquely determined. So not just like x1, x2, x3, and y1, y2, y3, and z1, z2, z3, but all of them are uniquely determined. Lastly, strong verification would be showing that the output z1, z2, z3 satisfies the product of the x number and the y number is the z number, right? So this is like showing that it satisfies some formal mathematical expression. So hopefully this clarifies what the exact difference is between weak, witness, and strong. Yeah. So now let me talk about what Ecne does. Okay, so Ecne will take in a set of QAPs that are verified, potentially nothing, by the way, that it uses like trusted QAPs. And then it will try to verify a new QAP. So the first step is using prior knowledge, where it finds instances of trusted QAPs within this input QAP. Then it will use an inference algorithm to verify that QAP. And as I mentioned before, this only supports weak and witness verification. Strong verification would require, I think, something akin to a theorem prover, and we did not do that. So a schematic as to how this works, you'll take your input QAP and a bunch of trusted QAPs. So this prior knowledge engine will simplify the QAP using what it has from the trusted QAPs, as well as creating some special constraints that I'll talk about on the next slide. Then it'll use an inference algorithm to try and solve this simpler QAP as well as these special constraints. So here's what prior knowledge looks like. How do we find a known good QAP and find it in some existing ones? So here's an example of a circuit. So let's look at y equals is 0 of x, okay? And this is something so that y is going to be 1 whenever x is 0, and otherwise y is always going to be 0, okay? And one can show that this is equivalent to the QAP, which is like there exists a z, so that y equals 1 plus x times z, and 0 equals x times y. Basically, if x is non-zero, then y has to be 0, and by modular inverse, there exists a z, so that this is true, a unique z, in fact. And if x is 0, then y can be anything, or y will be 1 because x is 0, and z can be anything. So that's actually a case where witness verification wouldn't be true, but it's still useful. So now if we see the constraints, y prime equals 1 plus x prime times z prime, and 0 equals x prime times y prime, like in some other QAP, we can instantly just replace that with y prime equals is 0 of x prime, as long as z prime is not used anywhere else, right?
Mm-hmm.
So now let me talk briefly about some of the algorithmic details about how we find these prior QAPs. To discover these good QAPs, the first step is to hash the sorted coefficients of each equation. Okay, so this equation we see as coefficients like 1, 1, 1, 3, 6, 1. So then we just like sort them and hash them. The sorting is done so that even if you like permute the exact variables, the hash will still be the same. So as long as you have equations that are essentially the same, they should hash the same thing. Okay.
Sorry.
So when
Franklyn, could you go back to? Could you illustrate the inside of this conversion in the sense that let's say you see an equation from existing, like a good QAP. So first of all, like how do you define the notion of good QAP? You mean they are known to be bug-free or?
These are QAPs that, so you provide QAPs that you trust, okay?
Mm-hmm.
And so maybe you trust like this QAP.
Okay.
And now you just look for that in other QAPs. And like, if you know that this corresponds to the is 0x, you can just replace like these constraints, like y prime equals 1 plus x prime times z prime, and 0 equals x prime times y prime. And you get y prime equals is 0 of x prime, right?
So you are trying to build an index from the QAP that you trust to the actual implementation of the second program. So I'm just
okay. I will show an example in the next slide, actually. So I think this should clarify something. Okay. So when you call a function in CirCom, the resulting QAP will contain the original QAP with just new arguments. So if you call if you have a function f and you call a function g, then the QAP for g will be present in the QAP for f. And this will actually only happen if you have O0 compilation, which means no optimizations. And then this will let you do like a substring match. Okay, so maybe you have your QAP, which looks like this. This is your input. So like x prime equals 3 times d, y prime equals 1 plus x prime times z prime, and a 0 equals x prime times y prime, and like y prime plus 3 equals x. Okay, now you like hash each equation, and you might get like, I don't know, 153, 462, 613, 316. Then you look at your QAP that you trust, which is this QAP I mentioned earlier, and it hashes to 462 and 613. So you see, oh, there's a substring match here, right? This 462, 613 matches this 462, 613. So you can just replace this with y prime equals is 0 of x prime. That's how this convert. Yeah.
I see.
You have a question about the previous slide?
It wasn't it was the slide. Oh yeah, right here. So can you talk about where this hash 11136 comes from? These numbers here?
Yeah, so I just looked at the coefficients of each like term here, right? So this is like 1 times x1, 1 times x4, 1 times x2, 1 times x7. I just took those numbers and I sorted all of them. I took all the coefficients. So you'd have like 1, 3, 1, 1, 6, 1 here. And then you would like, and then you would sort those into the list 1, 1, 1, 1, 3, 6. Then you would hash that and get 73,000 or whatever.
I see, but don't you lose the where the parentheses are? So for example, like where you're like, because wouldn't your multiplication change then? Say for example, if I had like x1 plus the x squared and then a parentheses times. Yeah. So how do you are we, because I'm assuming that then you could have two different equations hashing to the same set of sorted coefficients.
Absolutely, yeah. So this is not the only step that is used, right? So usually when you apply hashing, that's only your first step. So if I see these two things that match in substrings, like I'll flag that as a candidate, but I won't immediately do the replacement.
I see. Okay, and then we'll talk about other stuff like
so I actually didn't prepare anything to talk about that exact process, but once you have these exact things, you kind of just look at every single term, track like, okay, this variable like appears with these coefficients. And then you just do a very manual check. Okay, like if y prime appears in the first term with like appears on this side with a coefficient of 1 and that side with a coefficient of 1 and here with a coefficient of 1 and there with a coefficient of 1, you can just like look at all of them. You can just look at every variable and the coefficients it appears with on every single term, respecting parentheses. And then you can just use that to see if the substitution will work. This is just like kind of a find and replace thing.
Okay, makes sense. Thank you.
So frankly, we also have another question from the student in the sense that so right now you're assuming that all the prior like QAP that you pick are trusted, but what happens if you make a mistake and then you pick someone that you think it is trusted, but it's actually problematic? So what will be the consequence?
Well, if it's untrusted, you might prove that it's like weakly verified. You might show that something is weakly verified, like conditioned on these other things working. And that might just, and I mean, that's true, right? But it turns out that like the overall thing is not weakly verified because you trusted something that wasn't true. This actually did happen in one of the later examples. But does that make sense? Like you're saying like, okay, if I assume these things are true, then I can get this other thing. But of course, if you trust that thing, you might get a claim that's not true overall. Cool. So now let me talk about the inference engine and what rules it, how it works. So the key idea is that it maintains a variable state, which tracks the currently known information about every single variable. And this information includes things like, is it uniquely determined? So this will always be true for the inputs and 1 and none of the other variables, since we don't know if those are uniquely determined at the beginning. You'll keep track of a lower bound and an upper bound. And you'll keep track of an ABZ group, which is a group of variables with at most 1 not equal to 0, and you know which one it is. So if you know that like earlier I mentioned that you had a bunch of variables such that you knew like at most one of these was not equal to 0, and you could figure out which one it is. It just depended on some other value x. That would be an ABZ group. And you keep track of this information, and you also have a set of inference rules, which tells you how you update the state of the variables. So the simplest inference rule is like if k times z is unique and k is a non-zero constant, then z is also uniquely determined by a modular inverse. Okay, so some other inference rules. If ax equals b for an invertible matrix A and b is unique, then x is unique. And if x1 plus x2 plus x3 is unique, and as I mentioned before, these variables all belong to the same ABZ group, then you can show that each of these variables is unique. Right? So if you had like, this is because you know which one of these is non-zero, you know that one has to be the unique value and the other ones are 0. Okay, so that's one of the inference rules. So coming up with these inference rules is a lot of fun because you just kind of look at these problems and you're like, wow, what can I not show? What deduction do I need to make? And then you come up with whatever deduction you're missing. And you just program that into Ecne. So now I've described the rules. Yeah.
So one quick question. Frankly, is your current like a framework, like a parameter to the inference rule, in the sense that is there any way that I can, if I want to, let's say, enrich your current engine with additional inference rule, do I just need to fit those actual rules to you and then it just work out of the box, or do I need to make any additional changes?
You would need to change the code of the program. The inference rules are not like an input; they're just hard coded.
Okay.
But you could just, if you wanted to, you could just look at the code and add an inference rule.
Okay.
Although that is a very interesting suggestion. We have not really needed it so far since our inference rules have basically been sufficient, but I get that would definitely be cool for the future. Okay, so now let me describe how the inference algorithm works. So it works similar to a breadth first search algorithm. So we have a queue of a bunch of equations that we think are very promising, okay, and that we think these will give us like useful information. So for every promising equation, we will try every inference rule to learn about the variables. Okay, so maybe if we see something like this, we'll run this inference. If we see something like this and we don't know if z is uniquely determined, then we can immediately conclude that z is uniquely determined. Okay, and every time you learn something about a variable x, you just push all the equations that contain that variable, like y equals x squared, onto the queue, right? You should only process an equation if you've learned something new about one of the variables in them. Otherwise, if you didn't get anything last time, you probably won't get anything this time either. Okay, that's actually a very important optimization because it means that any equation is not pushed onto the queue very often. It's only pushed when you learn something new about it. And this leads to an algorithm which is actually linear time in the number of equations. So this observation was, yeah?
Wait, is this best case linear time or worst case linear time?
This is worst case linear time because every equation can only be pushed onto the queue like a constant number of times, right?
But is there any case that you have to like doing some like a fixed point computations, in the sense that I might not be able to like identify these particular optimizations, but and I skip in the previous iteration, but after I do something else, I explore more options, and then in this case I have to, like, some candidate could be like a push back and forth onto your queue. So that seems like a polynomial as opposed to like a linear.
So some comments about that. In general, with the variables we have, the reasoning steps, I guess, are relatively simple in that you only learn like more and more about like each variable, right? Like you never forget information about your variable. So there's like a constant number of things you can learn about a variable. There's like a constant number of things you learn about a variable. So every time you learn, say, oh, the variable x is bounded. Okay, now I push it onto the queue. Oh, the variable x is uniquely determined. I push it onto the queue. You keep doing this over and over and over again. And eventually you keep doing this, and basically the point is that you don't push these equations on very often. Like you only push this equation, y equals x squared, onto the Q if you learn something about y or you learn about x, right? And you can only learn something about x like finitely many times.
I see. I see.
Like
I see.
Like a constant number of times.
I see. I see. I see. I see. So could you elaborate a little bit about? Are you going to illustrate what you mean by promising equations?
It doesn't actually matter like what equations you use to begin with. Like you could just put everything on here if you wanted. The promising equations are just like that's not.
No, go ahead. Sorry.
So basically, I think it's hopefully it's relatively clear how you get the equations once you like hopefully it's clear how the algorithm works once I tell you how I initialize the Q, right? Because then you just go down, you look at the top thing on the Q, you try every single inference rule to learn about variables. And then you like push things on top, and then you push things to the back of the Q.
But are you saying that how you initialize the Q doesn't matter? Like for instance, like from my understanding, this is essentially a work list algorithm, right? This is essentially a work list algorithm in which you initialize some elements in your work list, and then you iteratively apply the rewrite rule, the inference rule that you collect. So in that case, my impression is that depending on how you're going to initialize your initial work list, it might lead to different performance. No.
So like the number of times you push something onto the Q is still like a constant, right?
Well, but constant can be large, right? It can, yeah, it's a constant, but the constant can
sure,
be large.
Like I guess the way like I guess like sure, it's like constant, but it doesn't depend on the number of equations. Yeah, like it could be large. In practice, ours are not large.
Okay.
But like in practice, this is linear time because yes, like in principle, you could, for example, you learn that this variable is bounded between 0 and 5, and you push it onto the Q. Then you learn that it's between 0 and 4, and you push it onto the Q. You learn that it's between 0 and 3 and push it onto the Q. But in practice, that doesn't really happen.
Okay. I see. Okay. So any other questions regarding the high level picture of all the inference algorithm before Franklyn move on? Just feel free to unmute yourself, speak out, or you can also type in your questions in the chat window. All right, I think we can move on.
Actually, there's a question in the chat I want to address. Vasilios, is that right?
Oh.
Have I answered your question? Does it make sense?
Yeah, it makes more sense now. Thank you.
You have any other questions? Like, I'm happy to answer anything.
I think so. Junrei has a question. Have any soundness and completeness result be proved on the inference rule in the sense that can you so I think Brian introduced the notion of soundness and completeness on Monday. So I think he was wondering what kind of guarantee that your inference algorithm can provide.
Okay, so my inference rules are all like right, but they might not be enough to prove like everything that is true. So they are sound but not complete, I believe is the right order for that. Mm-hmm. That's like these inference rules might not solve anything, but anything they do derive will be true.
Okay. Assuming that each inference rule is correct.
Yeah.
Is there any case that well, I guess this might not happen in your case, but it's any way that each individual inference rule is correct, but some combination of them might be wrong, depending on what assumption are you making for those inference rule.
So most of the inference rules are like relatively simple. They all look like this.
Okay.
So I don't think weird things like that should happen. They also all execute like atomically.
Okay. So okay.
Like I don't try to like apply multiple of them at the same time.
Okay. Sounds good.
Cool. So now let me talk about some of the results of our algorithm. So Ecne can witness verify with no trusted functions. It's like not trusting anything. 49 out of 76 of the circuits in circumlib. Okay, and circumlib is a bunch of circuits that are very commonly used. I can witness verify the ECDSA circuit given the strong verification of big mult mod P and big mod. Okay, so this is actually like 1 million constraints, and Ecne was able to process these in 10 minutes. It can also witness verify TornadoCash, which is a very popular protocol for sending money anonymously when we assert the weak verification of the Peterson function, which is an elliptic curve function from circumlib. Okay, and lastly, it can witness verify Hermez rollup main and weakly verify Hermez withdraw, which is a rollup, which is a ZK rollup without any assumptions. So now I'm going to talk about each of these results in a little more detail.
Okay.
So circumlib contains a lot of commonly used functions that are used in zk-SNARKs, things like hashing, things like indexing, like the example I showed at the very beginning, and Ecne is able to verify 49 out of 76 of these, most of which are relatively simple. But there are still some, right, that it doesn't verify yet. And here's one of them, okay? So this is baby add. Baby add is a function that takes 2 points on an elliptic curve and adds them together. So here you might see, this is saying that like beta is equal to this x1 times y2 quantity. So if all these inputs are unique, then beta is unique. Great. And gamma, delta, and tau are all unique. Okay, but now here's where it gets interesting. Look at this equation right here. You have that 1 plus d times tau times x out is equal to beta plus gamma. Okay, and when Ecne saw this, Ecne saw, okay, I know what d and tau are, so this is a uniquely determined expression. And beta plus gamma is also a uniquely determined expression. But what if x out, what if 1 plus d times tau here is 0? In that case, x out would not be uniquely determined. It could be anything. And I actually thought this was like a real problem. Like, did I find an issue with circumlib here? This could be a real problem, right? So fortunately, it turns out that according to this paper, which this comment that's added is mine, by the way, and theorem 3.3, they show that indeed 1 plus d times tau is not equal to 0, right? And this is a pretty complicated proof, and it would be somewhat unrealistic for like Ecne to really come up with it. And furthermore, like just to kind of give you an idea as to why this is hard, I can find values of x1, y1, x2, and y2 so that this division by 0 happens. It wouldn't be challenging. The reason that it doesn't happen is that x1 and y1, x2 and y2, these are all points that lie on the baby jub elliptic curve, right? That's why this function is called baby add. So that needs to be like stated as a precondition somewhere, or else by itself, this function is not actually like weakly verified. Is not weakly verified. In that you can get ways to have these like non-unique outputs. Okay, does this example make sense? And is it kind of clear why it'd be very hard to solve this case?
So one question. So when you say Ecne cannot verify, you mean that it raised a false alarm, right? So in the sense that like the ground truth for this baby add is supposed to be safe, but Ecne say that this is potentially unsafe. And then the reason that it feel that this is potentially unsafe because there is it cannot infer that 1 plus like d times tau it's actually can be non-zero, which is something that you cannot infer automatically. Okay.
This is so in this particular case, this is kind of a tricky one. So if you added like checks that x1 and y1 and x2 and y2 lay on the elliptic curve, then you could prove that 1 plus d times tau is not 0.
I see.
But right, however, like I agree that this by itself is not weakly verified, and that is like actually a pretty important note that anyone who uses this should like be careful to check first that these points lie on the curve, because by itself this does not provide unique outputs.
I see.
But even if we had this precondition, these points lie on this elliptic curve, we would still not be able to solve this. Like we still would not be able to, Ecne would still not be able to do this.
I see. I see. So I think we have a question from the audience about the divide by zero, which is also I'm not 100% follow. Could you elaborate?
Yeah, of course. So if 1 plus d times tau here were 0 and beta plus gamma were 0, note that x out could be like anything, right? So in that case, this would be underspecified. The reason why this can be 0 is because d and tau are numbers in a finite field. So it's possible for 1 plus d times tau to be 0 mod p. Does that explanation make sense? Or
so yeah. Oh, okay. So you're making the implicit assumption that it's also going to perform a mod p operation. So that's why you can potentially get 0.
Yeah, exactly.
Okay.
Yep.
Okay. Makes sense.
Because all these equations are over a finite field. Cool. So ECDSA is a function known as the elliptic curve digital signature algorithm. So this is for signing things, and it's very useful in Ethereum applications because Ethereum uses ECDSA. ECDSA has 1 million constraints, as I mentioned before, and basically uses all of our inference rules. Like all of our inference rules were needed to crack this one. And in fact, there's some components that are kind of beyond what Ecne is capable of. So I mentioned earlier that we can show that Ecne is ECDSA is weakly verified, assuming the strong verification of these other circuits. And this actually might seem strange. Like strong verification feels like it's kind of in the entirely different ballpark than weak verification. So why is this useful? And I think this has something to do with like an interesting fact of math. Sometimes you need to have very, very fancy tools to prove like very simple results. Okay, so like Fermat's last theorem is a very simple statement. It's like x to the n plus y to the n equals z to the n has no solutions in integers when n is above 3. But proving that is very, very hard. You have to introduce a lot of new things to do that. And likewise here, we'll use strong verification to establish weak verification. So earlier I showed you some inference rules. And basically the way all those worked was that they looked at an equation and they concluded that a variable was unique given a single equation. However, concluding that some variables are unique requires like a lot of equations, not just one equation. And if you have precise mathematical statements, you might be able to reduce the number of equations you need. So suppose that like these are not QAP constraints, obviously, like they're way more complicated, but that we had that like x1, x2, x3 times y1, y2, y3 was equivalent to z1, z2, z3 modulo p, that y was between 0 and p, that p was prime, and that x1, x2, x3 base b was not 0 mod p. So the way you would get constraints like this is through like strong verification combined with the prior knowledge I mentioned, right? So if you have like a multiplication mod p, which I mentioned is something we depend on, you get this constraint. Likewise, if you have strong verification of big less than, you get this. You don't just get something like, you know, z1, z2, z3 is uniquely determined given x1, x2, x3, and y1, y2, y3. You have that like this formal mathematical expression is true. So once you have that, you can now conclude based on like modular inverses that y1, y2, y3 is uniquely determined as long as x, z, and p are uniquely determined. And this is the key step in verifying that ECDSA works. Okay, so this is why you might need strong verification to prove results about weak verification. Because even proving things like this variable is unique require like, you know, formal mathematical statements to derive.
Okay, so Franklyn, I just want to make sure I understand. So when you say you verify ECDSA with millions of constraints, so you are doing weak, what you call weak verification. Essentially, you're checking the uniqueness of those variables, and then so you cannot verify, even for this weak verification, you cannot verify that alone unless your tool is essentially provided by those additional assumptions which you show in the current slide.
Yes, exactly.
And then those those assumptions are some like equivalence that is like a Ecne cannot be proved, but something that it would be nice that you have, if you can have. Okay, I see.
Yeah, so these constraints are not like, they're not things that Ecne can derive, because these are like formal mathematical statements that that are not like QAPs, right? They're not like simple, they're very complicated symbolically.
Okay, okay.
Okay, so TornadoCash, this is actually relatively well captured in what we had before. This is a protocol that's frequently used for anonymous money transfers, and it uses an elliptic curve method called Peterson, which is in circumlib, but very, very hard to verify. If you assume that it is weakly verified, however, we can basically witness verify all of TornadoCash.
So
and now we have.
So could you go back to the TornadoCash example? So in this case, so if I understand correctly, so because the majority of the components are first, like so when you say you verify TornadoCash, you mean you verify the circumlib code in TornadoCash, right? So
Yeah.
So the circumlib implementation for TornadoCash is not that complicated, in the sense that, let's say if you're already assuming that the Peterson's it's already like someone verified for you. So what will be the remaining constraint? Like, what's the size of the constraint looks like after you exclude?
I mean, even after you exclude Peterson, you still have like 600,000 variables.
Okay, okay. It's just like you still like verify everything, including the Peterson, but it's just like you just take, because like you're assuming that Peterson is verified, it's already verified. So that's why you include all those informations into what you call knowledge base.
Okay, even if you assume that Peterson is, this claim that like these things are trusted, I think, is actually like, I am saying that like these things are shown when like you have certain like pre-verified results, right? Like when you trust certain things. And a lot of these things, like people do have like good verifications for already, but I'll talk about that later.
Okay. So could you briefly like comment why this Peterson in the circumlib is hard to verify? Is that because of it is too big, or because of like the operation that it performs is super complex?
So size is like basically never an issue because we have linear time. Peterson is hard to verify because proving that it works, it's kind of like baby add. It's very similar actually.
Okay.
So like you need to be able to prove like mathematical statements that are like very challenging to show. Like showing that they work depends on a lot of fancy math, like not like just simple inference rules.
Okay.
That's why TornadoCash is hard to verify. Okay, and Hermez is a protocol that's used to make rollups using circuits. This is also now called like Polygon Hermez. And we were able to witness verify Hermez's rollup main and weakly verify Hermez's withdraw. This weak verification point is actually kind of important because we'll describe some of it now. So in conclusion,
Sorry, when you mentioned when you verify Hermez, so first, how complex is the circuit? And then second, so in order to verify, like just like what you call weakly verify, so you don't need any additional like assumption or input at all?
No assumptions are needed.
Okay.
Hermez is actually like relatively simple. At least it's easy to weakly verify. I'll kind of explain later why there could be some issues with that designation.
Sounds good.
Okay, so we have now shown like we can witness verification of several of like the most commonly used and complicated circuits, like TornadoCash, Hermez. These are ECDSA. These are all projects that are kind of pushing the envelope of what we can do with Circom. And Ecne has basically been able to verify all of them without even using like that much time, right? So is this enough? Like, is Ecne enough? And remember from before that as long as we have weak verification and witness satisfaction, we can show the equivalence of a QAP to a function. But we need both of those properties. So one potential limitation is, there are circuits that Ecne might not have the inference rules to prove, right? So maybe if we add more inference rules like you suggested, we'll be able to prove weak verification, witness verification of more circuits. For example, we might want to verify like baby add curve that I mentioned earlier, given the preconditions that are needed to make like that division by zero not happen. But this is far beyond the scope of what Ecne can do, because Ecne can only really run like relatively simple inference rules on like small sets of equations. For this particular task, there actually are other formal verifications. So this is a website, hyperelliptic.org, and this website shows off, this isn't shared anymore, but let me, so this gives you like explicit formulas, and it has like a verification script written in Sage that shows that these like division by zeros don't happen.
I see.
Since the baby jump curve is a specific example of a twisted Edwards curve, this is just all good. Furthermore, I think a lot of the formulas like Peterson and so on can actually be verified with Sage, so we don't need to verify them ourselves. So since most like programs are not really pushing like the frontier of algebra knowledge, it's not super clear that we need to have these more of these like algebra theorems. And this limitation is actually relatively minor then, because we can usually assume that most of these elliptic curve things will work if we just like look at math papers and look at like the Sage verification. Okay, so there might be buggy witness generation. So I mentioned earlier that even if we have weak verification, if we don't have witness satisfaction, that might be really problematic. Okay, so earlier I think I showed, so if the witness generation code does not generate valid witnesses, since Ecne can't really control that, Ecne only looks at the QAP, not at the witness generation code, we might not have witness satisfaction, right? So if you go back all the way here, if the y and z that are generated from X just don't satisfy these two conditions, then we won't have witness satisfaction. So if we don't have witness satisfaction, we don't have the equivalence. Hopefully you could catch this with a bunch of stress testing, but I guess it's possible that you couldn't. But this limitation is like kind of beyond our control. There's not much Ecne could really do here. So now let me talk about limitation 3, which is perhaps the most mysterious one of these, and that's called partial functions. So some functions are called partial functions, and this means that they only output things on a select set of the subset of the domain. So for example, if you have the square root function and you took the domain to be like all reals, the square root of -1 is like not a real number. Okay, so these functions, these functions can never be witness satisfied because for some x, they just won't produce any y. So weak verification showed us that y is uniquely determined given x, but that's not significant in this case at all. We have to show that there are no legal values of y, right? There's nothing that, because we need to show that no y is okay. Showing that y is unique is just not good enough. So to show that this is not just some like very like obscure corner case, let's look at these functions which actually kind of look a lot like what we saw in Hermez and TornadoCash, okay? And say that you have the function balance after payment, okay? And say that like A is the amount you pay and B is your initial balance and auth is some authentication. Okay, and this function returns B minus A if the authentication is valid and an error otherwise. Okay, because like this is kind of all paying someone is, but this auth is like actually really important. So a bad QAP for this might be given by like output equals B minus A. And this QAP, Ecne would be like, this is perfect, right? This is weakly verifiable. This is witness verifiable since we literally don't have any like other variables. But hopefully it's clear that this would not be equivalent to balance after payment. In some sense, balance after payment is just subtracting two numbers, and that's all there is. But it's also important that this authentication passes, right? So this is a partial function, and when the authentication is invalid, there's not supposed to be an output. And so witness satisfaction won't be true here. So you can't show that this is like, you can't show that this QAP is equivalent, this QAP given by like output equals B minus A is equivalent to this like balance after payment. And that's good because those are not actually equivalent statements. So this is a very hard case to deal with. There's a few ideas that we kind of had deal with this, but this is something that is likely quite challenging. So earlier you asked me about witness and like output and weak verification. Like why is it important that we have witness verification over weak verification? And that's because witness verification means we can like actually calculate the witness just given this QAP. And for example, one thing you might do at this point is you might try a bunch of concrete values for input X and then look at the values of the witnesses you get by solving the equation. And you know that this is possible because by witness along the way of, it's kind of about the process of witness verification, not just what you actually have from witness verification, not the result of witness verification. So you might be able to solve for the witnesses. And once you've solved for the witnesses, maybe you can see that, okay, there are no solutions in this case. And you might match that when the authentication is invalid. So you could do this in a lot, again, kind of a stress testing fashion. And Ecne will kind of make this possible. It doesn't really directly support this, but knowing the equation structure will help you stress test better. And of course, this approach is much more ad hoc, but for partial functions, even though we can establish weak verification like this, it may not extend to equivalence, especially when we don't have like witness verification. I think that was a mouthful, so I'll like take any questions now about this.
Okay, so I'm actually a little bit confused by the challenge here. So you're saying that so when you say partial function, you mean given these partial functions, first of all, like what's your definition? What's the formal definition of partial function?
It's when you have a function f that like sends some, it has a domain x and some output space and some range y, but for some values in this domain x, it just doesn't take on a value.
Okay, so in this case, in your case, could you elaborate a little bit more why so this balance after payment, which is essentially going to take 3 arguments, right? It takes 3 arguments,
yeah.
and then the behavior is it's either going to be b minus a if it's valid or error otherwise. In this case, so let's say this is the circon program I'm seeing right now, and then in this case I run Ecne on this code, and then you say that this is actually verifiable, right? And but what is the potential issues on this case? A bad QAP. So what do you mean by?
Here's like, this is a okay, so this is a QAP that like works, right? Output equals b minus a. This QAP satisfies like weak and witness verification. Output is uniquely determined given b and a. But if you remember the argument we had earlier, right? The earlier argument shows that if you have like a witness generation procedure for any x, you've shown that a unique y can work, and you found that y.
Okay.
But there might not be a y, right? That's the issue with partial functions. So showing that a unique y can work is just not enough.
I see. Yeah, that makes sense.
So in like, basically there's in the case of partial functions, there's just no way to prove witness satisfaction. So in these cases, you'll need like some kind of strong verification, or you can use this ad hoc method where you like try to solve concrete instances of X.
Yeah. You do either like you either checking
Yeah.
equivalence or you do like a ad hoc testing. Okay.
Yeah.
Okay.
And
Yeah,
one reason for this is that the other reason that I want to just elaborate again on is that we want to show that this is true for all X, like all valid numbers X, not just like valid authentications, right? Of course, like if you can impose like a stronger set of preconditions, like authentication has to be valid, then this QAP is correct, then you're good, right? But that has to be done in a very that has to be like that. You might need a precondition here. This is also, you mentioned earlier, like why shouldn't like the index lie between 0 and 2, right?
Yeah.
And that's how like, you could technically say that in that case, z of I is like a partial function. Cool. So now let me talk about how you might use Ecne in practice. So Ecne lets you home in on the exact conditions that might be tricky to verify. So say that you can verify A at trusting like B, C, and D. So in this case, it means that you just need to check B, C, and D, and you don't need to check like anything else, right? You just need to check B, C, and D. And as mentioned earlier, Ecne showed that ECDSA was witness verified, assuming that big mult mod P and big mod were accurate. And that means that if we wanted to verify ECDSA, it meant that we could just look really hard at big mod and big mult P. And in something of a pretty nice situation, we actually did find an issue with big mod, which is used in big mult mod P. Once again, the issue was a missing range check.
Wait, Franklyn, yeah, I was actually going to like use this as an example to ask you. So if I understand correctly, you cannot use Ecne to detect this problem, right? Because this is this is inside the big integer, like multiplications. Because
this
right
is
now
inside big mod, yeah.
Yeah. So right now in this case, if let's say if I indeed want to like use Ecne, it's on this big mod operation. So what's the problem that you are running into with Ecne? So if you run your tool, it's going to be say that this is a verify, or it's going to say that this is unsafe. What
I mean, Ecne is sound, so it's never going to say that this is wrong. It's never going to say that this is right if it can't prove that, right?
Okay. I see.
So the issue that's going to emerge is that basically there will just be too many variables moving around and showing, and like it's exactly the thing I mentioned earlier. You need to be able to like establish equations like these are needed to do some of the reasoning.
I see. Okay.
You need to spawn equations like that, and Ecne doesn't have the ability to do that yet.
I see. But if
like Ecne cannot output this. Yeah, but I do want to say this. I actually do want to mention something. So hypothetically, if you initialize Ecne in such a way so that you feed in some input variables here and some output variables, and you like look very specifically at this individual line of code, so you don't try to verify the entire function, maybe you verify like snippets of it, right? I think this is something that you could actually like hard code in as like a division rule.
I see.
So it can't verify the overall function, but I think for this particular issue, if you focused Ecne in on like this very specific part, like it won't work out of the box. But it will work that way. Yeah.
Okay.
So, but nevertheless, this showed that Ecne was able to do something like useful. It found, even if it couldn't find the bug itself, it was able to raise awareness as to like where any bugs would be, because it could tell you, okay, there's no bugs on this part of the area. You just need to check this part. So that was one of the things Ecne was useful on. So one way you might do debugging with Ecne is it prints out the values of variables that are unknown or not uniquely determined. And one thing you could do is you could just look for the first one that was unknown and then try using that to debug. So now let me show you a live demo that I prepared that will show us what Ecne is just like capable of. Okay, so let's first do a. Let me comment this out. And let's just do something like very simple. Okay, so like, let's just do the example we started off with. So this is saying that z is equal to x times x, and this is saying that y is equal to z times x. Okay, so we can run the compile, which looks like this, all good. Then we can run Ecne. So Ecne will show that z is uniquely determined, y is uniquely determined, and x is uniquely determined, so all good. Okay, now let's try to like mess something up. Okay, so again, we compile. Now we Now we only have one nonlinear constraint. And now we run this again, and we see that y is not uniquely determined anymore. So if we saw that, we could then look back at the code and be like, oh, I never defined y. That's an interesting problem, right? So this is something you could do with Ecne.
Cool.
Okay, so now let's show like a more complicated example, because this is like kind of straightforward. I think like most people could probably do it. Like it would be like, this is just very straightforward. So now let's like look at a harder case. Okay, so this is one in which we're using the ABZ machinery. So here like A is going to be, ignore these like arrow equations. They're just there so that the compiler doesn't complain. Okay, and here we might obtain like 0 equals like a minus 1 times e1, like 5. And here, because A is uniquely determined, here we know that E0 and E1 will form an ABZ group, right? And like at most one of these is going to be 0, and at most one of these can be non-zero, and we'll know which one it is. So if we know the sum, then that'll tell us E0 and E1 uniquely. Okay, then we just do some straightforward steps. Okay, so we need to compile first. Right, and you know, everything looks good. And if we just like say like comment out this statement, and we run this again, you get that it's false, right? And it'll show you the constraints that it has difficulty with. So namely here, it knows that like A was uniquely determined, but E0 was not uniquely determined. And you can look here to be like, okay, E1 was not uniquely determined. And 0 equals a minus 1 times E1. So this shows that this is like, hopefully this demonstrates that Ecne is both very fast and provides like helpful debugging output. Cool. So lastly, I just want to thank some people. I want to thank Brian, first and foremost, for introducing me to ZK and getting me really excited about this. I want to thank Yisun for always being at my meetings with Brian. I want to thank Wending Lee and the rest of 0xPark. Although I did not include his name here, I want to thank Antonio for helping me with, he made a lot of these open source, he made a bunch of fantastic open source contributions. So we did things like, so for example, originally Ecne wasn't able to get these variable names, and he was able to do that. He also set up a very cool HTTP server that you can send like your R1CS files to, and it will verify them. I want to thank Andrew Sutherland for showing me some of the formal verifications that already existed. I want to thank you, of course, for inviting me to this place, inviting me to give this talk to all of you. I want to thank Scott and his Scott Commoners and his research group, which I gave a version of this talk to. I want to thank James Rooney for looking over a version of these slides and giving very helpful comments. That's all, and I hope that was helpful, and I'll be happy to take any questions.
All right, yeah, so let's thank you, Franklyn, for the great talk. Thank you so much. Actually, I also want to thank you, like Brian, for giving us the talk so on Monday. And so yeah, so to answer like Vasileria's question, so yes, it's recording, and then we will share the slides after the talk. So any other questions from the audience? Like anything that you are unclear about the Ecne system, feel free to ask. So what's the next step?
So that's a good question. I think some of the next steps include being able to prove, like being able to state preconditions, especially like a lot of the conditions about elliptic curves. Maybe we can just like maintain a bunch of variables that we know lie on elliptic curves. And that could be like, in addition to variable state, which just states things about individual variables, we could use that to state information about a lot of variables. So we can have like better preconditions. We can try to state theorems. We can try to make functions that have like a precondition form. so they can handle these like partial functions.
Mhm, mhm.
Because at least at the very least, you could then say something like, okay, for all x for which authentication is valid, then this is true.
Mhm, 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 mhm.
So that would get you a version of like the QAP program equivalent.
I see. I see.
There's
And
also potentially like, still some performance improvements that could be made, but it's relatively fast already. So that's not as that pressing. And yeah, ideally, hopefully we'll be able to get like prove stronger forms of verification too, if we can like connect this with a theorem prover or something.
Yeah, yeah, yeah. And then another thing is that if you can make this kind of a rewrite rule a little bit parameterized, that will be, I think that will be like a very useful to extend your current framework, in the sense that, for instance, if I have to like approve a particular domain, I might need some specialized rewrite rule that might not necessarily like available in the original Ecne system. So if there's any way that I can plug in those rules without actually touching your original code base, I think that will be very useful, I think.
I see. Okay.
All right. So any other questions from the audience? We still have a couple minutes. All right. So if no questions, let's thank Franklyn again. And then let's thank our two speaker, Franklyn, both Franklyn and Brian, for giving us the excellent talk about ZK this week. Thank you so much.